In the problem that we're going to look at here, we have a cannoneer on a ship firing at an approaching pirate ship. The cannon is going to launch the cannonball at 115 meters per second, 25 degrees above the horizontal. The cannonball will strike the pirate ship 9 meters below the height from which it was launched, and we're asked to find everything. But before we start trying to find everything, our first step is always to draw a picture from the information that we're given. So the first thing that I'm going to do here is draw out my first pirate ship. So gonna simplify it a little bit here, and then we'll draw the enemy pirate ship. Maybe give it a little black flag so we know that ship is no good. Okay, so we take a look at the information that we're given here. The first piece that we're given is that the ball is launched at 115 meters per second. So if we have our cannon right here, then it will launch the ball like this. Remember, the path of a projectile is always going to form a parabola, and that's because of the acceleration only in the vertical direction. So from the problem, I know the initial speed that the ball comes out of the cannon is 115 meters per second. The next bit that we're given is the angle at which it is launched, so 25 degrees above the horizontal. So remember, that means we have to pretend that there is a horizon right here, and the angle that our speed makes with that horizontal line is going to be 25 degrees. So last bit of information that the problem gives us is that the cannonball hits the pirate ship 9 meters below the height that it was launched at. So if, let's say, this yellow line represents that horizontal line from which it was launched, then we know that the overall final vertical change will be 9 meters. And that's really all the information that this problem gives us to draw a picture from. So now we're asked to find everything. What is everything? First thing that we can do is take that initial velocity that we were given and break it up into its components. So we could find the horizontal part. How fast is it going across? We could also find the vertical component. How fast is it going up? And keep in mind that this is right when it is launched, because the vertical speed changes the whole time. From the information we're given, we'd also be able to figure out the cannonball's final velocity. How fast is it going at the end? And just like we did with the initial, we'll know that that final velocity is going to be made up of different pieces. One that goes across, the horizontal component, and one that goes down, the vertical component. And because we're landing or hitting the enemy pirate ship at a height that is not the same as the point where the cannonball is launched from, we're going to have to look for a different angle. So this final angle of the cannonball's velocity at the end of its trajectory. We'll also be able to talk about the maximum height that the cannonball reaches. Keep in mind it will be above that horizontal line that it was launched from. We weren't given enough information in this problem to figure out how high off the water. So keep in mind it will just be from this yellow line to the height of the trajectory. Probably the most important thing that we can get from doing all this work is the horizontal distance covered, the range. So how far apart were those ships? So this gray line will represent the range, and that's the big piece that we want to find, especially for this lab that we have coming up. And of course, along the way, we will have to, at some point, figure out how much time was the cannonball in the air? How long did this whole firing and hitting the enemy pirate ship take? So, since this problem gives us a VI, we're going to start there trying to figure out what the components of that VI would be. So, we know that overall, the speed that this ball launches at is 115 meters per second. We also know the initial angle that it's launched at is 25 degrees. And the problem also tells us that our overall change in height, this delta YF, was 9 meters. So it's 9 meters away from where it started from, but we have to remember that it ends below where it started. So it's actually down 9 meters from where it started. So what we want to do is take that initial speed, break it into a horizontal part to get Vx, and a vertical part to get Vy. What that means is we have this thing that's at an angle, this vector, and we know that it is 115 meters per second big. Also know it's at an angle of 25 degrees. This picture is wildly not drawn to scale. So let's figure out what is this Vx, this horizontal component, and the Vy, what's the vertical component. So if you look, all we have here is a right triangle. Horizontal and vertical are always going to meet at 90 degrees. So we have to bust out our trig functions for this one if we want to find Vx. Well, we can look at the triangle and see that Vx is adjacent to the angle that we have. We also have the hypotenuse of this triangle, so the thing that links adjacent and hypotenuse is cosine. So for Vx, we'll have Vi cosine theta I. So the angle that it's launched at here, that's going to be 115 meters per second times cosine of 25 degrees. Remember, when you go to plug this in your calculator, make sure you're in degrees. So I plug this in the calculator and I find that Vx is 104.2 meters per second. So it looks almost the same for y, it's just that when we're looking at y, the Vy, that's the side that's opposite the angle that we're given. So the one that links opposite and the hypotenuse is the sine function. So when we try to find the vertical part of the initial velocity, it'll look almost the same as the horizontal part. But we're just going to change cosine to sine of theta I. So that's going to be 115 meters per second, sine of 25 degrees. And when we plug that one in the calculator, we'll be looking at an initial vertical speed of 48.6 meters per second. And you can tell from looking at the picture that you've drawn and this triangle here that that initial vertical component does indeed go up. So it's okay that this number stays positive. So after you've broken down what you're given initially, there's really no certain order that you have to go in, but I feel like what we did just a second ago has put us in a really good position to start talking about the horizontal and vertical components of the cannonball's velocity at the end of its trajectory. So right when it hits the pirate ship, what is going on in that situation. So now we're going to look for VF, VX, VFY, and theta F. So to find VF, the only equation that we have to find VF is when we take the square root of Vx squared plus VFY squared. So we do have Vx squared. Remember, it stays constant the whole time. So whatever it was at the beginning, it'll be the same at the end. So we found in the beginning that Vx was 104.2 meters per second. Ran out of room there a little bit. Couldn't quite fit the unit in, but speed is always meters per second. So now we have to figure out what is the vertical part so that we can put them together and get a VF and a theta F. So to get the final vertical component of the velocity, we have to bring out one of our equations. The only one that we have the right pieces for at the present time is VFY squared equals VIY squared plus 2g. Remember, g is just the vertical acceleration, and that's coming from gravity. So 2g delta y, and since we're talking about v at the very end, we'll talk about delta y at the very end. Alright, so the VF here is squared. If we take a square root of both sides, remember to get the whole side, then we'll have VFY totally by itself. So it'll look like VFY equals, let's remember to start our square root. So we said for VIY just a minute ago that it was 48.6 meters per second squared. And remember, we have to square that. And then we add 2 times g, which you hopefully remember by now is always negative 9.81 meters per second squared. And the final change in height, remember that was given in the problem, it's negative 9 meters. So I had to leave out units here so we could fit everything on this screen, so sorry about that. So we plug all this in the calculator, 48.6 squared plus 2 times negative 9.81 times negative 9, take a square root of the whole thing, and we will get that the final vertical component of the cannonball's velocity is 50.38 meters per second. And I wrote that in the wrong spot. Let me get that cleared up here. 50.38. for the final vertical component. So now that we have that vertical component, we can go back here. We have Vx, we have Vfy now. So we're ready to figure out the overall final velocity. So that will look like, remember to start the square root, we have 104.2 squared plus 50.38 meters per second squared. Take a square root of that whole thing, and you will find the overall final velocity of the cannonball is 115.74 meters per second. So just a quick note before we go on any further into finding theta. It's important to remember that this final velocity should be negative because that's when the cannonball is coming down. So the vertical part should have that negative sign in front of it, something I overlooked a minute ago when we were finding that. So now we want to find the angle that the cannonball's velocity is at the end. So theta f. Remember, when we want to find angles, that's when we have to use our inverse trig functions. And we always want to try to use the oldest information that we have. Here that would be Vx and Vfy. Since we use those to calculate Vf, we don't want to use Vf in case we made a mistake in doing that. So to find theta f, we'll be using inverse tangent. And to get an angle with the horizontal, we always want the y component to be on top inside these parentheses. So Vfy divided by Vx. So when we plug in what we have, this equation will look something like inverse tangent negative 50.38 divided by 104.2. So you plug that into your calculator, and if you're in degrees, it'll give you negative 25.8 degrees, which seems really weird that you would get out a negative angle. But remember, in physics, negatives just tell you directions. So the way that we can interpret this is that the final angle is 25.8 degrees. The negative here just tells us that it is below the horizontal. So I'm going to put BTH. There's no way I'd be able to fit below the horizontal into that space. So instead of going up, the negative just tells us now it's coming down. In the next step, we're going to try to find the total time that this cannonball's trajectory took. So if you looked at the variables that you have available now and compared them to the equations that you have available, you'd find only three that would make any sense to use. One of them being the horizontal equation, which we don't know the range yet, our delta x, so we can't use that one. So that means we're going to have to find time vertically. So one of the equations that we look at would end up giving us a quadratic. You'll get the right answer, it's just a whole lot more work than it needs to be. So simplest equation that we could use here is Vfy equals Viy plus G delta t. You'll have to do a little bit of algebra here, so subtract Viy on both sides. And then we're going to divide by g on both sides. So delta t is all by itself. So with the numbers that we have, we're looking at delta t equals negative 50.38 meters per second minus our VIY was 48.6 meters per second. And we're going to divide that difference by our G, negative 9.81. I told you it would show up in every problem. So you plug that into the calculator, and we're looking at just over 10.1 seconds. So especially for the purposes of the lab that you're going to be working on in class for angled launches, this delta x, our range, is probably the really big part. This is the information that we really need. It's the whole reason that we're going through this whole process. So since we have no acceleration in the horizontal direction, we only have our one equation, Vx equals delta x, our range, over delta t. So rearrange it a little bit. I'm just going to multiply both sides by delta t. So my range, my delta x, is equal to the horizontal component of the speed multiplied by however much time went by. So the numbers we have here, my Vx is 104.2 meters per second. And I'm going to multiply by that time I just found, 10.1 seconds. So when you plug this into your calculator, you will find that the overall range is just about 1,052.4 meters, which I guess I picked some really crazy numbers because that is just over half a mile. It seems like a really long range for a cannon. Thanks, Obama. So in the scale that you'll be working in, pretty small scale in the classroom, you'll want to be a little more exact with your final answer. So this one goes down to the centimeter. You may even want to go a little bit further if you're really looking for that quiz exemption. So the only other thing that might be useful for us in describing this situation is figuring out what is the highest distance that the cannonball is able to reach during its trajectory. And in order to find that, with the information that we're given, the equation we'll be looking at is V Fy squared equals VIY squared plus 2G delta Y, and this time we're looking at Y max. So let's do a little algebra to solve for delta Y max. I'm going to subtract VIY squared on both sides. So I'll have VFY squared minus VIY squared. Then I need to divide by 2 and divide by G. And that will get me that delta Y max all by itself. So when we go to plug in, you have to remember that the highest point is not at the final point. So when we plug in VFY, we're actually talking about what is the vertical component of the speed at the absolute top, the very peak of this cannonball's trajectory. So at the top of any projectile's path, the vertical component of the speed is always 0. It's not going up anymore, and it hasn't started to come back down just yet. So it's not positive, not negative. The only thing that can't be either of those is 0. So we have 0 squared minus 48.6. It's still starting from the same place, so we can use the same VIY. And we divide by 2 times negative 9.81 meters per second squared. So we take those numbers, plug it into our calculator, and we get that the highest point above the launch point that this cannonball is able to reach is 120.4 meters. So we have officially found a value for every variable that we could possibly talk about while discussing projectile motion.